In today's lesson, we will explore complex zeros. At the end of the lesson, you should be able to utilize the conjugate pairs theorem to find complex zeros, as well as find a polynomial with given zeros, and find all complex and real zeros of a polynomial function. Let's look at these two diagrams down here at the bottom. Let's use what you know to figure out what this polynomial function might look like. If you look at this, you can see that we have 1, 2, 3 turning points. In this case, we know that we have degree of 4. So our highest degree is 4. Notice our two zeros, -2 and +2. What is our multiplicity right there? Since the function passes through that 0, we know that we have an odd multiplicity there. Well, how can we have a degree 4 and have two zeros that have an odd multiplicity? That brings us to complex zeros. Let's look at the second one. In this case, we have 1, 2, 3, 4 turning points, so we know that we have at least a degree 5. One of our zeros passes through once again, so this has to be an odd zero. So could this be to the 5th power? We'll be able to answer that question better if we examine complex zeros. Let's first look at the conjugate pairs theorem. If a zero of a polynomial function is a plus bi, and if you remember, that's a complex number where a is the real number and bi is the complex portion. It has the imaginary number. Then we know that if we have a plus bi, we have to have a complex conjugate of a minus bi. Let's think about why that is. Consider x squared equals -4. How do we solve for x? We know we need to take the square root. We also know that if we take the square root to solve for an x, we're going to get a plus and a minus. Well, what is the square root of -4? We can pull out the negative as a plus or minus I. The square root of -1 is always I. And now we can take the square root of 4, and that gives us 2. So notice, anytime we have a complex number, because we had to take the square root to find it, we're always going to have two answers, a plus and a minus. Therefore, conjugate pair theorem means that complex numbers always come in pairs. The fundamental theorem of algebra says that every complex polynomial function of degree of n is greater than or equal to 1 will have at least one complex zero. If we have one complex zero, we now know that we will have a pair, so we'll have two. Let's look at some examples. In our first example, if we have a polynomial of degree 5, whose coefficients are real numbers, and we have zeros at 1, 7i, and 2 plus I, based on what we just talked about, in addition to 7i, we would need the conjugate, -7i, and in addition to 2 plus I, we would need the 2 minus I. And now we have our 5 zeros. For example 2, we need to find a 4th degree polynomial if it has zeros of I and 1 plus 2i. Well, we know it needs to have 4 zeros, so the first thing we need to do is, like what we did in example 1, find the other zeros. Well, we know we're going to need a -I as the conjugate of I, and we know we're going to need a 1 minus 2i as the conjugate of 1 plus 2i. In order to find the 4th degree polynomial, we need to take the zeros and write them as factors. Our first factor will come from our 0, which is I, so that's x minus I. Then we have a -I, so that'll be x plus I. Looking at our other numbers, we have a 1 plus 2i and a 1 minus 2i. That's just a complex number, so we still write it as x minus the number 1 plus 2i. And then for our second one, we have x minus 1 minus 2i. Now we've written our polynomial in factored form. In order to write it as a 4th degree, we need to distribute all these binomials together. The easiest thing to do is to distribute these first two together because these are complex conjugates, and you can see that one is a sum and one is a difference. And if you remember that pattern, all you have to do is square the first term minus the square of the second term. Well, what is an I squared? If you remember, we said that I is the same thing as taking the square root of -1. If we square the I, and square the square root of -1, we can determine that I squared is just equal to -1. So, in this case, we actually have x squared minus a -1, which we can again simplify to be just x squared plus 1. How about these two terms here, or these two polynomial expressions? The first thing we should do is take the negative and distribute it into the parentheses. When we do that, we get fairly large expressions. We could distribute the x into each of these terms and then the -1 and the -2i, but that could be time consuming and it's easy to make a mistake. So instead, let's go ahead and use a grid to help us with our distribution. Now what we're going to do is take each of these elements and we're going to write them as a heading. So we have x, -1, -2i from our first polynomial here, and then our second one is x minus 1 and 2i from our second. Now all we have to do is multiply these together. X times x gives us x squared, and we can keep multiplying all the way through, -2xi, and then on to our second line. Once these are all multiplied, now we can move on to our third line. So we would get 2xi, -2i, and -4i squared. Once we have this, we can start to simplify. 2xi and -2xi cancel, -2i and +2i cancel. I squared, remember, is -1. -4 times -1 will give us +4. Now we can write what we have left. So we have x squared plus 1, and then based on our grid, we have an x squared. We have two negative x's, so -2x, and then we have a 1 plus 4. We almost have our polynomial to the 4th degree. We just need to distribute these two polynomials together. We could do another grid, or we could do it the other way, where we distribute each element to each element. I'll go ahead and do that just so that we have some variety. And now we're on to the 1. 1 times anything is just going to be that anything. And then finally, I would just need to combine my like terms, so I would get x to the 4th minus 2x cubed plus 6x squared minus 2x plus 5. And that's my 4th degree polynomial. Let's look at a different type of an example. In this example, we want to find all zeros and classify each as an integer, non-integer, rational, irrational, or non-real complex, given this function. Where do we start? We don't have any zeros. We know there's going to be 3, but we don't see anything. In this case, we can graph this function and try to pull off the integer real zeros. Here's my graph of this function, and you'll notice that I can only see one of the zeros at 2, 0. Sometimes you may graph a function and you may see some other zeros, but you'll notice that they will be irrational numbers, meaning that they'll be decimals that continue on and they don't repeat. They're not rational. In that case, you can't use those. So the only thing that you can pull off from a graph are the integer real zeros. Well, in this case, we can pull off 2, 0. We'll start with that. What we want to do, our first zero is a 2, and we can classify that as an integer. We'll just label that I. But we have 2 others. So the easiest thing to do is use synthetic division to factor out the 0 and see what's left. Using synthetic division, I will come down and I will see that I get a 0 remainder. Now I should always get a 0 remainder if indeed 2 is a factor. If I do not get a 0 remainder, then 2 is not a factor. Now I can write what I have left. Remember that we have factored out 1x, so we no longer have a cubic function. We have a square or quadratic function. So we're left with x squared minus 6x plus 13. In order to solve this, I can try to factor, or if I can't factor, then I can use the quadratic formula. And if I look at this, I can see that I can't factor this evenly, so I'm going to need to use the quadratic formula. Plugging the numbers into the quadratic formula, this is what I end up with. If I simplify, I can see that inside my radical, I'm going to have a negative number, 36 minus 52. That equals negative 16. So now I'm ready to simplify that even more. 6 plus or minus 4i over 2. 2 goes into 6 3 times. It goes into 4 2 times. And here are my other two zeros. So I have 2, and then I have 3 plus 2i and 3 minus 2i. We can classify these as the non-real complex. So non-real complex. And I know I'm finished because I've identified 1, 2, 3 zeros. Let's look at one final example. Same thing. Find all zeros and classify them. Go ahead and pause the video and see if you can try this problem on your own. Remember that you may need to graph this in order to try to pull off a real integer zero. For this problem, you can see 1, 2, 3, 4 zeros. So we know that none of our zeros are going to be complex zeros. However, if we look at this zero, this is a decimal. So at this point, we have an irrational number. Here we have a negative 0.5. That's a rational number. We can use that. Here is an irrational number, and here is an integer. So let's pull off the negative 0.5 and the 6. We can actually use both of those. What I'm going to do for this problem is I'm going to use synthetic division to factor out both of these zeros. So that will drop my quartic down to a quadratic. And from there, I have many methods of which I can solve, including quadratic formula or factoring. So how do I factor out a negative 1/2 using synthetic division? I'll use the same technique that I've been using this entire time. Make sure when you're using synthetic division that you consider that you're not skipping any degrees. And so far we haven't had any placeholders that we'd need to apply because we have fourth, third, second, first, and then our constant. So using synthetic division, 2 times negative 1/2 is just going to be negative 1. And then adding these together, negative 12, half of negative 12 is 6. Putting these together, we get negative 6, positive 3, 36, and then negative 18. Notice that once again, we have 0 as a remainder, so we know that negative 1/2 is in fact a 0. Okay, now we can use 6. So let's go ahead and keep these where they are. We don't need to build a function yet. These are our new coefficients, and we're going to factor out a 6. So we can do the same thing. Bring down the 2. We have 12, 0, negative 36, and we end up with 0. Now we're ready to build our quadratic. We have 2x squared. We don't have a middle term, so we don't have an x, and then we have minus 6. Now we can solve this. So x squared is equal to 6 over 2, which is 3. So here is where our irrational numbers come into place. How do we solve x squared equals 3? We take the square root of both sides, and we get plus or minus the square root of 3. Plus and minus root 3, those are both irrational numbers, but I have found my 4 zeros. I have negative 1/2, which is rational. I have 6, which is an integer, and then I have plus and minus root 3, which are both irrational numbers. And that concludes our lesson today on complex zeros. At this point, you understand the conjugate pairs theorem, and you can use it to help you find complex zeros. You can find a polynomial function with given zeros. You can also find complex and real zeros of a polynomial function.